In this video, we will use both Excel and Minitab to perform a one proportion binomial test to test whether the observation of 37 female frogs out of a total of 50 frogs is more than would be expected by chance if the individual probability that each frog was female was 0.6. We start in Excel by calculating the probability of observing specific numbers of female frogs using the null hypothesis of a probability of 0.6. So we enter the total number of frogs, 50, in D2, the probability that each one is female, 0.6 in D3, and we will use the binomial probability distribution, which is given by binom_dist in Excel. So to start in C6, we will calculate the probability of observing exactly 15 females. And to do this, we will enter the binomial distribution function, which requires the number of observed, which is 15 in B6, the number of trials, which is the total number of frogs, 50, the individual probability, which is in D3. We do not want the cumulative probability, so we enter force, giving an individual probability of observing 15 female frogs as 1.249 times 10 to the minus 5. Now we're going to copy this calculation to all the other rows, but we need to lock the row reference to both the total number of frogs and the probabilities in D2 and D3 by using the $sign, and then we can copy this to all these other possible numbers of female frogs, and the chart now plots these probabilities for each of the specific numbers of possible observations of female frogs, showing, as we would expect, that if the probability of a female frog is 0.6 out of 50, the most likely number observed will be 30. For this particular test, we want to calculate the cumulative probability of observing either 37 female frogs or more. So we need to add up all of these probabilities from 37 onwards, and to do that we'll just copy these values into an adjacent column. So we need to add up the total area under this upper tail from 37 onwards. We can do that just by adding up the values that we've calculated so far, giving a total probability of 0.0280. However, this is not absolutely accurate because it doesn't take into account the very low probabilities of observing 46 or more frogs. Just for completeness, we can calculate this total area of the tail more exactly by starting with a total area of 1 and then taking away the cumulative area up to 36 female frogs. And for this cumulative area, we will again use the binomial distribution up to 36 frogs, again with 50 trials, with a probability of 0.6, only this time we will select the true option. So we are taking away the cumulative area up to 36 from 1, which will give us the tail area from 37 onwards. This gives us, to 4 significant figures, the same value that we have already calculated. This then is the probability that we could observe 37 or more female frogs by random chance. This value of 0.0280 is then the p-value for this one proportion test. To calculate the two-tailed value, we will have to add up the probabilities of observing 22 or less female frogs, so we can perform a similar calculation at the lower tail, this time going up to 22, and just taking the simple sum again, this gives us a lower tail area of 0.0160. These values are not the same in this case because this is not a symmetrical distribution. But then the total area of 0.0160 plus 0.0280 giving a p-value of 0.044. We will now see the same results obtained using the Minitab analysis. We can use Minitab to perform the one proportion test by going to Stat, Basic Statistics, One Proportion, and we have to choose whether our data is given as raw data values in a column or summarized data. And we are actually using summarized data, so we select summarized data, and we enter the fact that we have observed 37 events out of a total possible of 50. That is, 37 frogs were female out of a population of 50. And we wish to perform a hypothesis test to compare our observed proportion with an expected proportion of 0.6. We then also have to select options, and we can choose whether we have a two-tailed test or a one-tailed test, either proportion less than the hypothesized value or greater than. And in fact, we're testing that our observed proportion is greater than 0.6, so we select a one-tailed test, and under method we can either choose the exact calculation using the binomial distribution or a normal approximation. So we can start with the normal approximation and then just run the analysis, and here we observe the hypothesis that the null hypothesis is that the proportion is equal to 0.6, and the alternative hypothesis is that the proportion is greater than 0.6. We see that the analysis measures the sample proportion of 0.74 and calculates a Z value of 2.02. It also calculates the p-value based on this normal approximation test of 0.022, which, being less than 0.05, suggests that we should reject the null hypothesis and say that the experimental proportion is indeed greater than the 0.6. We can also return to the analysis to carry out the exact test, so we go to one proportion again, back to options, and now we will perform the exact test, which uses the binomial theorem. And again, the hypotheses are the same, but using the exact test, we get a p-value calculated using the binomial distribution of 0.028, which again says that we should reject the null hypothesis.